Good day, statisticians. Here is a follow-up video to our first video where we introduced how to come up with an exponential equation when we had this exponential relationship between two variables. Previous in our course, we'd only looked at linear relationships, and now we're finally at the point where we can deal with nonlinear relationships. And the only thing we've so far seen is exponentials. That last video was very mathy. Its goal was to help you try to understand exactly where these equations come from. In this video, it's much more practical. We're just going to, again, recap. I'm going to find the exact same equation that we found before using the logarithmic transformations, but here we're really going to look at just how to use the equation to make predictions. It's fairly simple and straightforward, but that's really what you're going to be expected to do if you were actually being assessed, not all that fanciness that we saw yesterday, or we saw in our previous video. So here again, we have this situation where we are comparing the ages of people's ages with the amount that they would be asked to pay for $1 million term life insurance policy. And so what we had seen in our last video, we'd seen that in fact the relationship between these two variables was an exponential relationship. This is exponential. And so in order to come up with an equation for the exponential relationship, we learned that we had to do a logarithmic transformation. And this logarithmic transformation, well, essentially what we do is we kept all the x values exactly the same. Remember, x was the age, right? X remained exactly the same. But we'll plot the x values not against the premiums themselves, but against the natural log of the premiums, right? And what we found is that when we plotted this relationship, that was actually a linear relationship. There was a linear relationship between the ages and the natural logs of the monthly premiums. So that's where we're getting our equation for an exponential equation. So let's get to let's find that equation again in this video, just very quickly. Right? So the key was that we took our our values in L2, and we're going to take the natural log of them and paste them into, and paste the natural log of the values in L2 into L3. So what I just did is I just calculated the natural log of all these insurance premiums. I put them in L3. Now, to get the equation is I'm going to make the least squares regression line. The fundamental principle is this. Let's find the least squares regression line for, that says for, this guy right there. Let's find the least squares regression line for if I was to plot the x values against the natural log of the y's. To get that least squares regression line, I just go to my calculator, hit stat, go to calc, go down to option 8, because again, we're doing a linear regression with a transformed set of data. We'll do L1 with L3, we'll hit calculate, and shazam. Boom, it shoots out a linear equation. Now this linear equation, right, is the linear equation. Now, to make sure you always save space, because we have to write out lots and lots of terms on these linear equations. But notice that in the calculator it just says y equals ax plus b. We need to remember that we're not dealing with a linear equation in terms of y. We're dealing with a linear equation in terms of the natural log of y. So we'll write the equation as the natural log of y hat equals. All right, then the y-intercept was 0.15099, and then we'll add to that the slope. The slope of this relationship was 0.0812, actually 30 if I rounded the correct number of decimals. And I don't know why I kept that black and this guy red, but whatever. So this guy here is our y-intercept. This is our slope. But again, this was the relationship if we were to plot the x against the natural log of our y values. And we're ending up getting this sort of linear relationship like that. Okay, so here's the fun fact. In the last video, I took this equation and I converted it back to something that looked like a standard exponential function in the form a times b to the x power. Now, that is not required here. We do not need to actually take this equation in terms of the natural log of y and convert it over, that should be a y hat, of course, convert it back to an exponential. We're perfectly fine keeping this just in this form in terms of the math that we want to do, right? So let's do some math. Let's do a nice little a simple question, right? Personally, you guys want to guess how old I am? You probably know how old I am. Me, this guy right here. There's me. I am 39 years old. getting kind of old, right? My age is 39. So for me, the X value for myself would be 39 years old, right? And so how much should I pay if I was to get $1 million term life insurance monthly? Well, if you look in the table, 39 is a little bit less than 40, so it's probably something kind of like between 21 and 30, probably pretty close to 30. So if I wanted to know, I could just figure it out by plugging it in the equation. So how would I do that? Well, that's simple. I go to my calculator. I'll put in 0.15099 plus 0.0813 times my age, 39, and I get that. Now, what did that produce for me? When I plugged that X value into this equation, what I actually got is not the insurance premium. I'm not going to pay $3.32 per month. I wish I would definitely get that insurance. No, instead, what that produced for me was the natural log of the predicted insurance premium that I would get for someone my age, right? And that, the natural log of the prediction is 3.32169. Now, I recommend you do basically no rounding here. This is a very practical video. At this point, there's no chance you want to do any rounding if you can avoid it, because when you undo this to get the y hat, if you just want to solve for y hat itself, the only way to solve for y hat would be to take e and raise it to this power that we had right there, right? We'll have to do e to the 3.32169, that's a 1, power, right? So I'm going to go to my calculator, and so here, rounding, any bits of rounding will end up yielding dramatically different answers. This is exponential stuff. In fact, I'm lazy. I don't want to actually write it. If I hit second natural log, e, and I just hit up, I can paste that guy in, and I get my predicted insurance premium is $27, and I'll round it to the nearest cent, 71 cents. It predicts that my insurance, my term life insurance $1 million policy would be $27.71 per month. That fits with what I saw. It's some value that was a little bit less than $30 because but you know, it's still decent. So that's a pretty good guess. Now, we could use this equation to make all kinds of guesses, right? Let's say I was to try to make a guess. Let's say someone was starting to get old, right? I mean, is 65 old? 65 is pretty old. But let's say here, let me erase this. I don't really need this right now. Let's say I was to try to make a prediction for someone who was, I don't know, 70 years old, right? What would this line predict? Well, I could see what the line would predict. I could go and do the same kind of thing. Let me go up here. I'm just going to copy and paste that and make that 70, right? And then I found that the natural log of the prediction would be 5.84199. So I could just do, all right, let's do e to that power. And so now it's predicting when someone's 70 years old, we expect that the insurance premium will end up being $344.46 and things like that. Now, that's nice. And here's just a question I have for you. Which prediction are you more confident in? Are you more confident in the prediction for how much my insurance premium would be for me being 39 years old, or for the insurance premium of this 70-year-old person? Which of these two predictions to you is the more reliable? Think. Definitely the 39-year-old. Why? Well, do you guys remember when we talked about the concept of extrapolation, right? And that's something that we need to be concerned about even here, right? Where we talk about extrapolation, right? Extrapolation is where you start to make predictions based on values that are outside our original data set. So when I'm making a prediction for somebody who is 70 years old, right, here's 70, then that is older than the oldest person here. Can I trust that? Well, so long as it's not too far off from our stuff here, I would certainly be more confident in a prediction of a 66-year-old than I would of a 70-year-old. But I'd be more confident in a prediction based on this data of a 70-year-old than I would be of a 90-year-old. I don't necessarily know that this pattern is going to follow adequately outside of this data set. So always be mindful of extrapolation, regardless of how we're coming up with our equations. Okay, so that's the essence of things here. That's the most basic kind of stuff that you expected to be able to do in AP Stat. To be able to go and take an equation and make some predictions based on it. We will see one more video where we're also going to learn about a different kind of nonlinear regression. The other kind that you'll have to deal with sometimes in AP Stat is a power regression. And we're going to take a look at how we can analyze, again, residual plots to try to determine which is the most appropriate model for a set of data, whether it's an exponential or power. But we'll see you in another video, guys. Have a beautiful day, and I'll catch you on the flip side.